All right, so let's get started. So today we'll finish the process and interrupt parts. Actually, there's just very few about the interrupts, how does it work? And after that, we'll talk about the memory management. Okay, but before that, I think let's go through some Q&A. And actually, there are a lot of Q&A, so I'm not able to go through all of the Q&A, so I just pick several. I think it is more representative ones. And like if your questions like does not be answered on this list, and if you are really want some answers about your question, you can come to me after the class. So the first one is about thread. So the definition is here. Actually, just like executes within the same program in a shared memory address space, and usually open files, patch tables, those kind of things, they are shared between threads within the same process. So last time people are asking about, because in Linux there is a function called clone, and clone is very similar to the fork function. And the difference is like actually clone can control about which kind of resource can be shared between threads. So actually like this clone-vm is about those threads can share the memory address, and fs is kind of the like file system and files, and then some signal like these kind of things. So actually those kind of parameters in this clone function means what kind of resource you are going to share between process. Okay, so there is one interesting thing is about in Linux, actually we say the threads that they share the resource, they're not using the copy on write because they really share the resource. I mean, they really share the patch table. So even there is some thread modifies the patch table, all the threads can see this change. Okay, so copy on write is for the process because process has their own independent resource. So when one process is going to fork another process, actually they will do copy on write to avoid time-consuming data copy. But thread, actually, they are all shared and they're not using copy on write. So even one thread modifies some shared resource, there's no copy on write there. Okay. So also there are some question about like in Linux, actually, you cannot really see thread or process in the, for example, in the Linux source code. And the reason is because Linux coded a task. Because if you still remember, like at the very beginning, we say like in Linux, we call the PCB as the task dash structure, right? So task dash structure is going to describe the process and thread. So Linux code a task and it refers to both process and threads. And the difference between process and thread, I mean, in terms of the task, is about how much of resource they are shared between this kind of instance. So process have their own address space, but threads within a process will share the same address space. Okay, so they are all called tags, but the difference just about how much of the resource they can share. And the second question is about the CPU mode switching. So like before switching to kernel mode, CPU will automatically set essential register on the kernel stack, because people are asking about, hey, when we are going to switch from the user mode to kernel mode, and how about those kind of user related kind of register, those kind of things. And actually those kind of things will be stored on the kernel stack. So each process has their own kernel stack, and usually the size of the kernel stack is around 2 to the 3 of the patch size. So you can think about each process, they will have the kind of 8 kilobyte to 12 kilobyte of the space they're allocated for kernel stack. So when they're going to do the when they're going to do the mode switching, then those kind of user related register will be stored at those area. Okay. So the goal of CFS. So actually, like we talk about the goal is fairness and better interactive. And last time I said not real time. I mean like not hard real time, because CFS cannot provide hard real time. Hard real time means like for each process, if they are hard real time, they will have a deadline, like they should finish in what kind of a time. It is hard real time. So there is no room to be delayed. But CFS can approach soft real time. I mean, if there is a little bit delay for some process execution, actually CFS can do these kind of things. Okay. Oh, and there's another thing is about the reason like CFS cannot approach hard real time is because if we're going to meet the hard real-time requirement, usually it means to let some high priority process occupy CPU aggressively. So when one process can get a full kind of load of the CPU, it means like it's possible it can meet their hard real-time requirement. But actually, for some other process, if they are not like high priority process, they cannot get any CPU. So actually, there is some contradiction between the hard real-time and then you're going to make it fair. And the last one, I think it is quite, I would say, like interesting, but I mean, this part will not be, I mean, on your exam. I just want to share some kind of information with you. Like people are asking about software and hardware context switch. So actually, software context switch is the things you learned last week. Just like you, I mean, when there is a process, they are going to be rescheduled, and operating system will do some like schedule MM and then schedule to function to switch the address space and switch a process. And those are called software context switch because most of the flow, they are controlled by the operating system, and operating system is kind of software. So it is called software context switch. And actually, there's another thing called hardware context switch. So hardware context switch is like CPU's hardware mechanism, or like you can think about there are some circuit designs that can go through the context switch flow. But actually, it is not a context switch. They are wrong in the operating system base. I mean, there are some lightweight context switch that can be run inside the CPU. So there is an instance is about most of the CPU now they support hyper-threading code. Okay, so hyper-threading is just like there is one hardware code, but actually they can pretend as two software cores there. So when you open the Linux and then you type like TOP, the top instruction there, and actually if you press 1, you can see there are a lot of cores there, right? And the number of cores will be more than the hardware cores you have in your CPU. And the reason is because that top information that exposed to you is about including the hyper-threading part. Okay, so that's about too much, but like I'm going to let you know, like hyper-threading, they use a hardware context switch to switch between two hyper-threads. Okay, so but yeah, there are too much details here, so I just skip the hardware context switch for now. Okay, so actually there's another question is about the CFS, but I think that is super important. So let me do some clarifications on the past following few weeks when we talk about the CFS. So I think the main goal and the concept there are all the same, but today I'm going to use an example to let you understand how CFS works. So there's one thing that I do some modification here. So actually let me define two things. The first is about the allocated CPU time. So you can think about if there are n processes that are in the run queue, and then for all the process, the total time to run all the process, let's say is this kind of schedule period. Okay, so you can think about schedule period if it is 6 milliseconds, then in this 6 milliseconds, we need to serve all the n process in the run queue. Okay, but the thing is like each process has different priority, right? So there is a calculation is like nice k weight is about if there are there are k here. You can think about there are k process in the run queue, then we sum up all the weights among those k process, and then this nice dash weight is about each process. What is the weight value of each process? So if you are confused about what is the weight here, so actually weight is just like this. So there is nice value from -20 to 19, right? So for each nice value, you can get a specific weight. So for example, -20, you can get like at 761, and for the nice value 19, you can get a weight value like 15. So these are weight values. So coming back. So after doing this calculation, actually it's just about to allocate the maximum CPU time for each process. Okay, and then I slightly modified this theory kind of formula because last time I forgot this clause. Actually, the V runtime will be add on to the prior virtual runtime. Okay, and most of the things actually they're the same. So let's just directly jump into the example. So one example is like if there are two processes the first process called process 1, second one called process 2, and process 1's nice value, let's assume to be 0, and then process 2 has like kind of nice value 19. And actually, we are going to first calculate the allocated CPU time first. So actually, P1 and P2, if overall they can have like 6 milliseconds, for example, then we can do like 6 millisecond times, because processor 1 nice value 0 is 24, like this. This is 0 here, so this is 1024, and 19 here is kind of 15. Okay, so 1024 over 1024 plus 15. So P1 at most it can run for 5.9 milliseconds of time. Okay. And on the other hand, like P2 should be like 6 milliseconds times 15 over 1024 plus 15. So it will be around 0.1 milliseconds. Okay. So according to their nice value, or like according to their priority, actually processor 1 will get more CPU resource because it has higher priority. Okay. So this is the like ideal case, or like you can think about the maximum CPU that can be allocated for each process. So let's start for running the two process. So at the very beginning, we will do the initialization. So each virtual runtime for each process, they will get 0. Okay, because this is the initialization. So all the virtual runtime, like no processes run before that, so they'll get 0. So P1 will run first usually because P1 is getting higher priority here. So if P1 after 1 millisecond, if P1 fetches the IO, then because fetching the IO, so we need to switch off P1, right? Because when there is an IO, so we need to do a process context switch. Okay, so after doing the process context switch, actually there's only 2 processes here, so we will switch in process 2. Okay, so after switching process 2, if there is an assumption is if after 0.05 millisecond, P1 finish the IO serving. I mean, for example, P1 get the data from the storage device now, and P1 is back to the run queue. Okay, so here comes the case. Should P2 keeps running, or like should we prioritize P1? So for CFS, we do this calculation. Actually, we need to calculate the virtual runtime. So the virtual runtime is here. So delta dash execution means how long does this process run? So you can see like for process 1, because it runs for 1 milliseconds. So here's 1 and times nice dash 0 dash wait. So dash 0 is about we need some kind of wall time, or like we need some baseline. So usually this calculation, like we will take the nice dash 0 dash wait, that is 1024 as our, I think it's kind of nominator place. And then for nice dash wait here is about the wait value for that process. Okay, so for example, for P1, for here, nice dash wait will be 1024, but for P2 here, nice dash wait will be 15 because the nice value for P2 is 19. So this wait value will be 15. Okay, so after doing some calculation, you will find like, hey, actually the P1's virtual runtime is only 1, and P2 actually it gets 3. Okay, so according to the CFS, these numbers will be updated to the red-black tree. So after the update, actually, we'll always pick the smaller one to reschedule. So 1 is smaller than 3. So P1 now can preempt P2. Okay. So actually P2 only run for 0.05 millisecond and it will be preempted by P1. So P1 can come back to run to use up the rest of the CPU resource. Okay. So this is the example for the CFS. Okay. Okay. So that is for the CFS part. Then let's keep doing the recap part. So we talk about like process context switch, and we also define what is process context. Actually, you can think about it's just an environment to run a process. So it includes user address space, just like patch table, hardware register, just like the program counter, and then those kernel data structure, like kernel stacks, those kind of things. Okay. So we talk about like process context switch. Actually, they include 2 kind of component. One is called switch-mm, and it is going to switch the virtual memory mapping. And then the other is switch-to function. It switch the process stats. So we talk about the details about like switch-mm, what kind of things they are included. So I will skip here. And we also talk about switch-2, but actually the main key concept is when you are going to do a process context switch, you need to switch the virtual memory mapping and then the process state. I think this is the core part that I'm going to let you know. Okay, so system call part. Actually, last time we quickly go through the system call, and then the idea behind system call is very similar to interrupt. So this is the reason we don't talk too much about system call. Okay, so system call, you can think about it is a way for application to signal or like to run the kernel service, because when application they are running in the user space, they need some way to interact with kernel, right? And system call is one way. Okay. So how to signal the CPU to run the kernel? Actually, there's a things called software interrupt. Okay. So software interrupt means if CPU run the instruction called int $0x80, it means CPU now needs to run the it is an interrupt instruction, and we need to run some system call service. Okay, so after running this instruction, actually CPU will, from the user mode, will be changed to the kernel mode, just like this. Processor A now is in the user mode, but at the time like the CPU run this instruction, CPU will dive into the kernel mode. Okay, and there is another parameter is what kind of system call that we need to run. Actually, there is a system call number. So according to a number, for example, number 0, for example, maybe it is read, and maybe 1 is kind of write, for example, like this. So inside the system call table, there is a way for the CPU to know where is the source code for this kind of corresponding system call number. For example, system call number 0 means, for example, is a read operation, but we need to know what kind of things we need to do for this read operation, right? So we need to find where is the code of this for these read operations, and then we will check the system call table to get where is the code is, and CPU can run the code. Okay. After running the system call, actually CPU will get back to the user mode and then keep running on the user process. Okay. Okay. So we also talk about like that is software, and now there is hardware events here. So there are 2 hardware events for CPU to work with the store hardware device. So one is called porting and another is interrupt. Okay. So porting is the kernel will check hardware status periodically. So for example, for every like 1 millisecond, kernel will stop all the things and then to check, hey, if the IO is finished, like these kind of things. And interrupt, on the other hand, is that the hardware device to signal to the kernel. Okay, so let the hardware device send a message to the CPU to let the CPU know the hardware device is finished. Okay, so we talk about like what kind of things will cause, like how the interrupts be called, and hardware device will physically produce electronic signals to the CPU. Okay, so CPU can directly get the information. And then we also show you like the example, like, hey, if there's a motherboard and then there's North bridge and South bridge, and usually like South bridge will be connected to several different kind of slower hardware device like keyboard, hard disk drive, and PCI SSD. Okay, so when we are going to do the interrupt, actually keyboard, hard disk drive, and PCI SSD will send a signal, an electronic signal to the CPU. So CPU can know it is now interrupted by what kind of device. Okay. Okay, so same as system call, actually interrupt, there are also according to their number. I mean, different interrupt number, different interrupt value, it means different interrupts. Okay, so there are 256 interrupts number usually. And like, for example, for like IRQ0, it means like the timer interrupt, IRQ1, just like the keyboard interrupt. So different numbers means what kind of device and what kind of service it is going to do. Okay, so we also show you this last time. I think this is not quite, I think it's not quite like important, just that you know current systems, they are using this kind of mechanism to map the interrupt vector number and the interrupt request. Okay. Okay, so I think we stopped at a prior page, and today we are starting right here. So how an interrupt works. So we put back our example figure here. There is a motherboard and there are south bridge memory, CPU, and south bridge connects to several kind of device like timer, keyboard, those kind of things. And they are connected by the cable. So you can think like for timer, there's a cable to the interrupt controller, and it is called the IRQ0 will be sent through this kind of cable. Okay. So let me give you an example. So if now you type something on a keyboard, actually keyboard will send a signal to CPU, and a signal will stand by this cable. Okay. So for example, because we know keyboard, the interrupt, sorry. So we know like the interrupt request for the keyboard is IRQ1, right? So inside the interrupt controller, actually, interrupt controller will help to translate the IRQ1 back to the interrupt vector number. So with this number, CPU is possible to know which interrupt it is now. Okay, so for example, IRQ1 will be mapped back to INT0x81. Okay, so like this. So like this. This is 0 at 80, and this is master PIC, right? So keyboard is the second one. So you can think about the second one is like 81. Okay, so there is a mapping between this interrupt vector, this interrupt vector number and this interrupt request. Okay. So with this interrupt vector number, actually the interrupt vector number will be sent to the CPU's kind of like interrupt controller. You can think about like this. So the key thing is actually our goal is, so where is the program, where is the location of the program? Because we now know like there is a keyboard interrupt, but what kind of things will CPU do to interact with this keyboard interrupt? So actually there is a piece of code, right? There's a piece of code to define what should CPU do to interact with this keyboard. And where should the CPU get the piece of code? So CPU can get the piece of code by using this interrupt vector number. So like this. Actually inside the memory, it will be striped into, or you can think about, it can be partitioned into several slots. So each slot, you can see there is a address. Actually, this is just an example. I mean, in the real system, you will not start from 0x0 usually. You will start from any other place, but I think it will not be 0x0. But this is just an example. So for example, like 0x81 now, we need to find where is 0x81. Okay, so actually for each slot, it is 4 bytes. And the reason for 4 bytes is because inside each slot, you need to store two kind of things. One is like code segment, another is an instruction pointer. So with using the code segment and instruction pointer, we can know what is the first instruction of the keyboard code. Okay. So 0x81 will be multiplied by 4 bytes. So now we can get 0x204. Okay. So CPU will fetch the data from 0x204, and inside the data, actually, there is a code segment and an instruction pointer. So with using this code segment and instruction pointer, actually, we can get where is the code for serving this keyboard interrupt. Okay, what is the beginning of the code is. So actually, like for example, CS plum, IP plum, maybe it points to this location, and CPU will come back to read this location. So after reading this location, actually, inside this location, there is a pointer to point to the starting point of this keyboard driver, like these kind of things. Okay, then CPU can run the keyboard driver. Okay, so like here is the code of ISR. Okay, and then CPU will keep executing like maybe IS. Here is 82, 83, 84. Okay. So this is the way like how CPU handles this kind of interrupt service. So question. Okay. Yep. Okay. So there's a question is why not just directly get a code? But the point is, what is the size of the code? I mean, because different interrupts, they have different size of the code, right? For example, keyboard interrupt, maybe it is about 200 line of code. But maybe rewrite operation, there's 1,000 line of code. So you cannot really know where to get the code is. So you need some interaction to get the first instruction of that code. So you can start to execute it. Yeah. The reason is like, if there is, I mean, if the interrupt code there have different sizes, then you cannot really know where is the starting point for each interrupt. Because it depends on how the operating system and the BIOS, how they decide where to put those code on. So we need some interactions to point to the beginning of the code. Yeah. Yep. Okay, so let's move on. Okay, so actually, the code of interrupt service routine, each interrupt service routine you can think about is kind of a piece of code to serve each interrupt. For example, ISR maybe like ISR 0 is for like read operation, and ISR 81 is the code to serve the keyboard. Okay, so this is about ISR. Okay, so interrupt service routine or interrupt handler is the function the kernel runs in response to a specific interrupt. So usually ISR is part of the device driver, like inside the kernel code. And here comes a challenge. Usually when the CPU is running the interrupt service routine, it is non-blockable. So non-blockable means that it cannot sleep. Because if it sleeps, then the CPU cannot get back to the original user process. So CPU will stuck there. So CPU should finish ISR and then return back to the original process to keep the progress. So the thing is, but if this like interrupt service routine is a super long code, or like it needs to do a lot of things, then the system will block there to wait for the finish of the ISR, right? So for example, if now you have a kind of network card and you are going to get the data from the network card, but actually maybe you only need the very few, maybe 2 or 3 bytes for the network card, but actually the overall size of the network package is like several megabyte there. Then you need to wait for several megabyte to finish, and then you need to wait for CPU to process on the several megabyte, and you can do another things. So in this case, Linux kernel splits the ISR into 2 parts. It is top halves and bottom halves. So top halves means to run immediately upon receipt of the interrupt and performs only the work that is time critical. So you can think about, because the interrupt service routine is super huge. So maybe there are several things that we must run at this moment, and they will be split into top halves. But the rest of it, it is not that time critical. We can postpone, we can delay it. So just like this kind of bottom halves part. So for bottom halves, work that can be performed later is deferred until the bottom half. Okay. So here's an example. The same, there is a network card receive a packet. So for top halves, it moves the packet from the buffer in the network card to host memory, because usually the data package will first be moved on the network card, right? From the other network card. Okay. But if you don't move the data from the network card to the host systems, then this network card cannot serve for other requests. So we need to move it from the network card to the host system first. So then other all the requests can be sent to the network card later. Okay, and bottom half is like what are you are going to process on those packets. For example, you need to decode a packet, right? You need to decide what kind of things you are going to do on a packet. But this is not like time critical because you will not block any later device. It only depends on the process you are going to do on this packet. So it is possible to delay these kind of things until the next time that process is going to process the packet, then we can resume it. Okay, so this is about the bottom halves. Okay. Okay, so that is about the process and interrupt. So then we'll move on to the memory management part. Okay, so here are the agenda that we will cover for the memory management. Actually, it will be mainly split into two parts, the physical memory management and the virtual memory management. And if I remember correctly, for the undergraduate operating system, we do not really talk too much about the physical memory part. Most of the time we talk about the virtual memory. So I put some things maybe it is good to you to know for the physical memory here. So I will talk about the physical memory first, and then following on we'll talk about the virtual memory part. So if we still have some time, we can talk about some research topics that relate to this kind of process and memory management. Okay. So at the very beginning, the same things, we need to talk about some basic concepts of memory management. So there are two things for memory management. One is called patch frame and another is called patch. So patch frame is the CPU will partition physical address space to chunks with the same size. And a patch, it means CPU will partition virtual address space to chunks with the same size. So the difference is the address space. There are physical address space and there are virtual address space. But I think it is not easy to understand what's the meaning for virtual and physical. So physical, you can think about the location where the data stored on a device. So because now we usually use DRAM, right? So if we have a 4 GB DRAM, then how to partition the DRAM? How to know where the data is stored on which place? Okay, so the address on DRAM you can think about is a physical. But virtual, it means the location where the programmers think the data is. So it doesn't relate to what kind of device it is, because programmer doesn't really know what is the address on DRAM. Not even DRAM. I mean, for example, like currently we have swap, right? The same things, like programmer doesn't really know the program is now on the DRAM or on the storage device because we haven't swapping. So it is possible maybe the data now is on DRAM and later on it is on the swap device, but programmer doesn't know. So for the virtual, actually, it's just about what does programmer thinks. Okay, so we'll have more details about the virtual probably next week. And this week we'll first talk about the physical things. So there are more kind of details about the basic part. So like this, actually, if this is a DRAM, okay. So if this is a DRAM, and then if we are going to do the partition, you can think about like this. So the whole DRAM is just a linear space, like if it is the 4 GB, and then we will divide by a lot of 4 KB patch frame, for example, like this. Okay, so normally people are using 4 KB now, but I mean, it depends. I mean, it is possible to use larger if you are going to use it. Okay, so the thing is, but this should be in the same size. Like this is 4 KB and all of them should be in the 4 KB. Otherwise, there are some fragmentation issues there. And we'll talk about the fragmentation later. Okay. So actually like, if this is a DRAM, actually there are some places they will be allocated for the kernel, and there are some places they were allocated for the user process. Okay, and we will talk about this later. Okay, so let me give you a quick example. Like, because when we are writing a C program, there is we frequently will call the memory allocation function, right? The MALOC function to get the memory address. So if P1 calls MALOC functions, the memory allocation function, then the kernel allocates patch frame, for example, like this. the allocated one, and then kernel will update the patch tables. Okay. And then CPU running P1 will work the patch table to get where is the location of the allocated patch frame. Okay. So this is the simple example, like how is the connection between the memory allocation and then to all the patch table things. Okay. So actually this example, you can also think about, last time we talked about there is a mailing address and then there is a like the absolute address layer. It is the same things. You can just use the same example, put it here. Okay. So kernel manages all patch frames and maintains patch table. So there are several things we need to know. First about how to manage each patch frame. And then the second one is how to do the allocation. So what do I mean for how to manage each patch frame is, I mean, in the Linux, how can Linux have a data structure to manage those patch frame? What is the data structure and what kind of information will be inside that data structure? And how to do the allocation, you can think about like this. If this is a large space and if there are several processes there, then there are some processes they will allocate and there are some processes they will return their space to the operating system, right? So how to do a good allocation? You guys maybe learn about like fast speed, burst speed, and warp speed, right? But how about Linux? What kind of allocation does Linux pick for this kind of allocation? Okay. Okay. Oh, so that is for physical part. Actually, there is another side is for the virtual memory management part. So for virtual memory management, just like it let all processes share the same physical address space via patch table, right? Because come to think about, if you in your computer you just have one DRAM device, for example, one DRAM DIMM is kind of 4 GB and you only have one DRAM inside, then but you have 10 processes they are running simultaneously. And actually those 10 processes, they use the same DRAM, right? Usually you will not say one process you can get only 400 megabytes for that process, right? So all the process will share the DRAM resource. So in this case, how to manage these kind of things? Because some process maybe it is like memory bound or like memory hungry, so it needs more memory, it needs more patch frames. But maybe there are some processes that are CPU bound. I mean, they only need very few patch frames. So how to do this kind of dynamically management? And those are about the virtual memory management. So here are some kind of thing is a basic knowledge that you need to know for the hardware part. So actually inside CPU, there are two hardware components. One is called TLB. I think it's kind of translation local site buffer, and the other is MMU. So when CPU is going to get the data from memory, actually CPU needs to know the physical address of the memory, right? But actually, currently, when the CPU get the instruction from the code, they're all virtual address. Because programmer only know the virtual address, same as compiler. Compiler only know the virtual address, right? And now if we are going to get the physical address, we need a translation between them. So CPU will first check a TOB. So TOB, you can think about it's just like a very small cache. Inside the cache, the cache content is the translation result for each virtual address. Okay, so you can think about TOB inside. There are a lot of this virtual address is translated to that physical address. Okay, but actually there are too many of these kind of entries. So TOB probably will not be able to hold all these kind of translation results. So you can think about maybe there is only 1% of the translation result that can be stored in the TOB. Okay, so first of all, CPU will check the TOB. If CPU cannot find the virtual address in the TOB, so CPU needs to do it by itself. But if CPU can find the TOB entry, I mean, the virtual address is inside the TOB, CPU can directly get a physical address. CPU doesn't need to do any further things to get the physical address. So with this physical address, CPU can directly access the memory. Okay, so if the virtual address is not in the TOB, CPU needs to do the patch table walking, and then CPU will send this will move this virtual address to the MMU. So it is called memory management unit. So actually MMU is not a very complex component. You can think about MMU, most of things MMU do is to do the offset and then to add some integer to another integer. They're just very simple operation there. Okay, so what I mean for simple operation is actually MMU, we're going to go through the patch table. And the reason to go through a patch table is currently Linux, they are using the 4 label patch tables. Okay, so I mean, in the undergraduate textbook, there are a lot of different kind of paging. I mean, there's kind of only one patch table paging. There are also several multi-label paging, those kind of things. But in Linux, they are using the 4 label paging. Okay, and we'll have go into the details. I think it's next week. I'll tell you like how MMU do this kind of 4 label paging things. Okay. So after doing this kind of 4 label patch table translation, actually MMU can get a physical address. Okay, and using this physical address, CPU can get the patch data. Okay, and then because the virtual address is translated to the physical address by the MMU, so usually MMU will store this translation resource into the TOB. So next time if there is a same virtual address inside the CPUs, the TOB, I mean the CPU can find the result in a TOB. Okay, so there is a very important thing because inside the CPU they will run different kind of process, right? So the things I'm not talking now, they're just only for one process. So each process, they will have their own patch table, right? So because they have their own patch table, so inside the TOB, they will only store for that process. So now when you are going to switch to another process, it means the TOB cannot be used for the next process, right? Because the TOB store the translation result, and the translation result is related to the patch table. But the patch table can only be used by the process that are running now. So when we are going to do the context switch, we need to switch the TOB, we need to switch the patch table. This is the reason. Okay. So, question? All right. So, okay. So let's move on to how to manage patch frame. So I think this week we only focus on the physical part. Maybe next week we will talk about virtual. Okay. So actually, if you learn like if you take the computer architecture course, maybe you will know there is a key phrase called byte addressable. Byte addressable means like current memory they're using the byte. I mean the smallest granularity to do the addressing is the byte. Okay, but actually in the operating system or like in most of the system now, like there is a things called patch, and patch is 4 kilobytes. So actually 4 kilobytes is larger than 1 byte, right? So actually we need some management to manage these kind of things because byte addressable in only for the physical part. I mean the physical address part inside the device. But for CPU, usually we will look at this kind of things as a patch. Okay. So if we are going to manage this patch, we need some data structure. So inside of Linux, there is a data structure called structure patch. Okay, so this patch, usually there are more kind of fields, but I only get some, I think it is quite important things here. So for the flex part, you can think about they are talking about status. For example, if this is the dirty patch frame or like it is a locked patch frame or not. So dirty usually means like the patch frame is, that means the data inside the patch frame, they are updated. Okay, so the reason like it is called dirty is because for DRAM, usually the data will be moved from the secondary storage, like the hard disk drive or SSD to the DRAM, right? And the reason is DRAM is volatile. So volatile means that if you shut down your computer, all of the information, all of the data inside DRAM, they will volatile. Okay, they will not be there. Okay, so if the patch frame is dirty, it means when you are going to shut down your, for example, computer, you need to write back this kind of data to the non-volatile device, like hard disk drive or solid state drive. So you can make sure the data, they are all in the latest version. Okay, so this is why there is a 30-bit there. Okay, and also there are some other things like if the patch frame is locked or not. And then the second one is dash count. So simply just how many reference there are. So I mean like how many like process or like how many threads they are using this patch frame. So this one is highly related to the fork function. So if you still remember, when we are doing the fork, we will do copy on write, right? Because we don't want to copy out the patch frames at the same time we call the fork, because it will take too much of time. So we say at the time we call the fork, we will do copy on write. We only do the copy when the data is updated. So the same things, when you do the copy on write, the dash count counter will increase by 1. It means there are two processes, or like there are more processes they share this patch frame. Okay, so when the patch frame is kind of updated by the child process or the parent process, we will copy out, we will do a private copy. So at that time, the dash count will -1. It means that process get their own copy. Okay. So actually, there are some other things that we did not talk about early, but I think maybe later on, if you are interested in, maybe you can get some information from the networks. Like there's a concept is called patch cache. So patch cache is usually for file. What do I mean for file? You can think about in a storage device, maybe you will store a lot of like movie or music files, right? But when you are going to like play the music or like play the movie, actually the data should be moved from the memory, sorry, to be moved from the storage to the memory. Okay. But do you think about like, have you ever think about like if there are not enough space for the memory, we need to pick some very frequently used data in the memory, right? So that is for patch cache. So the file that are cached in the file, so the file that are cached in the memory, they are called patch cache. And usually if you only have 1 GB of like memory and you are going to open up a lot of files there, then the system can only cache few of them. So those patch frames, they are related to the storage device, related to the file. There is this kind of patch cache structure there. So we can use the patch cache structure to find out where the data is. Okay. So because there is a patch cache, so there is a question is about, I mean, the file is usually larger than 4 KB, just like movie is several gigabytes. So one movie will be partitioned into a lot of, I would say like kind of million of patch frames there. Okay, so which patch frames is for which data? So there is an index in there. Okay, and then like there are some kind of information for the patch replacement policy, because like there is a LRU head here just to maintain if the memory is not enough, we're going to throw away some patch frames, like these kind of things. What kind of we're going to throw away some data, then what kind of decision that we are going to make that is about patch replacement. And then there are also a virtual address, just like the patch virtual address here, to know where is the like virtual address is. Okay. So actually, this structure patch is quite huge. And then, for example, if there is kind of 40 byte for each structure page, so you can just count, for example, this flex, maybe it is a young side long, so maybe it is a like 4 byte, for example, and this is 2 byte, this 2 byte like this, and you sum up all this kind of information, you can get each structure patch is like 40 byte. Okay, but like each structure patch can represent one patch frame. So for the 4 GB DRAM, actually we require like 40 megabyte of the information just for this data structure. We need 40 megabyte there. So yeah, I think this is not that huge, but it still takes some kind of overhead here just to maintain the information for each patch frame. Okay, so some basic concept of memory allocation. So initially, all memory is available. What I mean, all memory is like all the patch frames, they are available for user process. And you can think about like because it is not used, so it is considered one large block of available memory. Or like in our textbook in the operating system concept, it is called a hole. So when a process needs memory, the system searches the state of a hole that is large enough for this process. So there is a thing called first fit is to search and allocate the first hole that is big enough. Okay. But the thing is like, this is just big enough for example, if now you need a 4 megabyte, but the first hole is like 4 gigabyte, the system will still return the 4 gigabyte to you, even like this is a very wasteful decision, but this is first fit. So you get the hole larger than you want. And best fit is to search all holes and allocate the smallest hole, which is big enough. And the overhead is time because you need to search all the holes to get the best fit. Okay. And then the worst fit is to search all holes and allocate the largest one. It wastes both size and time. Maybe you are thinking about and why do we need worst fit, right? So the reason I say waste size and time, especially for size, is at this moment it is a waste for size. But because our system is running, so no one knows the future. So for example, for the worst fit, for example, if the process now they are asking for like a smaller like memory space, for example, 1 megabyte, but if the system give it like 10 megabyte, it does a waste now because we waste for a 9 megabyte. But maybe several moments later, maybe this process used up to 10 megabyte. Then in this case, if you use the worst fit to allocate that 10 megabyte before, then you don't need to reallocate the new space for that process. So in the future, maybe it is a good, maybe the worst fit will become the best fit, maybe in the future. So it is hard to say. Okay. So, yep, I think let's take a 10 and come back later.
这个为什么是1020啊？就是那个 nice euro 底线位置。
因为这个的0的时候，那是没有0，它是1024。
哦，所以那为什么这个Siri 它的公式是这样？就是为什么是？
因为他要拿一个人当基准点，所以他是拿 nice value 0，然后作为基准点去算。
哦，
就大家跟 nice value 0比，你如果优先度比较低的话，那你就你的 virtual runtime 通常就比较大，你就拿的资源就比较少。可如果你的优先权是比较高的话，你比 virtual 0，你比0这个基准点还要来的高的话，优先权的话，你就会拿到比较短的 virtual runtime，你就可以比较长拿到资源。所以它其实是个相对的，它是相对顶这个 nice value 去做。
哦，
对，所以公司里面才会是用0。
好，然后我还有一个，就是这个 ISR challenge 是这个 non-blockable 是什么意思？
就是它不能被中断。今天如果这个 ISR 它需要的是要做一些 IO 的事情的话，它也不会被中断，它就在那边做，它就在那边等。
哦，就干等。
对，就干等。
哦，
对，所以这也是为什么现在会出现说应该把它区分成2块啊。那如果很慢那一块啊，它可能就不要干等，它就不做这样子。所以它配的就是给那种它很重要、必须要做，它就算要等也要等的那种去做。
哦，对，哦，再看一下。就是他这个老师这边可以再讲一下嘛，就是他这里是
就是
CPU 会先去
TM，CPU 从程式码拿出来都是虚拟位置，
对，
但是机体是实体位置，
对，
我们要知道实体位置在哪里的话，需要透过一个转换，那这个转换呢，基本上它如果转换完，其实是可以先暂存起来的，因为这个转换是固定的嘛，就是这个 virtual address 转到那个 physical address 是多少是已知的，只是说因为它很多，所以它没办法就是全部都记下来。那今天如果我有机会是给你一个很小的空间，但是我可以先把预先抄起来在哪里的话，那就是 TOB，就给你一个小抄啊。那你有这个，只要在这个 TOB 里面，就不需要再做转换了，因为它都已经转好，过去就已经转好了。 对，那如果没有的话呢，那就是 NMU 现在现场直接帮你直接转。
哦，好，
对。
然后最后一个问题，是这个 mapping 是可以再讲一下这个 struct address space
哦，
mapping，
其实这个只是讲让大家知道说，这个资料结构之后会跟我们后面讲的会有个叫 patch cache 的资料结构是有关系的。然后 patch cache 的意思就是说，你今天如果要读一个档案的话，那当然是不是要从是硬碟里面读出来，读到记忆体里面去。
对，
可是你读完之后，基本上就释放出来了。可是今天如果你隔个1个小时，你又要再读这个档案的话，它又要再从硬碟里面拿。
哦对，
所以如果我要暂存它的话，我需要在记忆体里面画一个空间出来，那空间叫 patch cache。
哦，好，谢谢。
对，这样。
刚刚跟他的问题有点像，我一样看不太懂这边的公式跟这边对不对起来。
好，这边的公式的话是，哦，不好意思，这是旧版的，因为我的新版的时候有稍微修了一下。好，但是基本上这边的公式其实就是 delta x 就是你现在跑了多少时间这样子。
都实际执行。
对，实际执行时间。然后你这个 nice dash 位的这个地方啊，在新版我稍微做了调整，它这个地方其实是会需要有个基准点，所以它是跟 nice 0去做基准点。对，所以在新版后面是这个地方是完全改掉，是 nice 0去除以你当下这个 process 它的 nice value 是多少。
所以是 nice 0除以
对
这个 nice value，不是 nice k weight。
对，nice k 位是就是我又拿了一个式子出来是，那还是 nice k 位的。对对对，这个你再帮我确认一下新版。
记得啊，nice k weight 是用来算实际的。
对，哎，没错没错，nice k 位是来算理论上，如果我今天就给你6 millisecond 的话，那你要跑多久？
哦，然后
对
virtual time 是用另外一个
我当是在讲的是他正在跑的时候，因为正在跑的时候他没办法预知未来他可能会哪里会停掉，哪里会怎么样，所以他需要去做一个动态调整，说谁预测说你现在跑多久，那我是不是应该换掉了？
哦，所以后面有调过。
对对对，最新版的调过。对。
好，当资源足够的时候，但是它的 timer 还是到了，那它还是要被切掉再切回来吗？还是
你说如果他没有 IO，只是 timer 到而已。
对，
会，就是 timer 到的意思就是他已经用完今天他这是宣告可以用的时间了，所以不管有发生什么事情，他基本上都会换掉。对，当然他今天换掉之后，如果他是高优先权的人的话，他可能很快又会有 time slice，他就会这样 preempt 其他人。对，但是如果一般正常大家的优先权都一样，或者是他用完就要换别人用。对，他这个是
我这个6ms 什么意思
6ms 就是假设今天有10个 process 的话，它会设定一个 time 的 period。说这个 process 在这6个 millisecond 里面都要跑过一次，
就是偷执行时间。
对，应该说就是这6 millisecond 里面每个 process 一定要跑一次，但至于每个 process 跑多久还不管，就是让你有更好的互动性。
所以这是就在设计作业系统的时候会跑。
对，其实它不一定是6 millisecond，这只是个举例而已，它可能是其他不同的值，对，但它就是会有这样子的一个设定在那边。就如果你今天 process 跑很多的话，就是如果有10个 process 的话，它就不会是6 millisecond。
我等我一下。所以他是这样，我之前整理 Intel 收到指令 IRQ1，然后停止工作，他要先读 vector table。这里是什么 register 比较像是什么东西
？register 就算是一个就是暂存器，就是 CPU 里面会有一种，就是怎么讲呢？就像你可能程式码会变出成很多个指令，这个指令可能就是例如最简单好了，就是一个加法指令好了，所以你把2个资料把它加在一起，好，那资料传哪？资料就存在暂存器里面，
不是 cache。
哦没有，暂存器比 cache 更接近 CPU 里面。
那确实
对，就是 cache 是在，比如它的核心外面有个 L3 cache，然后还有 L1、L2、L1，但在运行的过程中，它需要有很快的存取速度。那种很快的存取速度，它就会仰赖于这种很小的，就是它可能一个暂存器可能就代表2个 byte 或4个 byte 而已。对对对。
刚刚详述一下，就是说，我有就是他说，因为他说这个 size 不一样嘛，所以刚刚意思是说，可能我代表 T
就是
有1000行，
对啊，
我要知道是哪里开始的地方。
也不用，就是好，我今天假设它这个有200多个不同的程式码，
对，
那每个人都不同 size 的话，那我全部都把它放在机体上，我怎么知道谁是谁？就是我怎么知道 从第一个位置到150位置，它是哪一个 code？那个是从150到第2000多，到底是哪一些 code？
他没有在先抓位置，再
对，因为抓位置的好处是你之后这些 code 如果重编啊，然后位置换掉啊，它都可以改这个里面的机体位置就可以了。
我也没在懂，所以它两个是分开来的，这
对
都是记忆体吗？
这都机条，
不是记忆
只是存的东西不一样。这机体里面存的东西是
体。
它要跑那个 code 的第一行的位置在什么地方？
哦，就是说这个是存位置。
对。然后后半段的那个是存，它真的是程式码，
然后这边是 code，这边是
对，它是 code 的。对，
所以它是有点类似一个这边 is， 哎，
这其实只是
这是一个
它是 vector，
content 吗？它是一个目
没有，这只是让你们大家知道说，这只是第一个位置里面是存 ISR0的机体位置，然后这是 ISR1它的第一行 code 的机体位置在什么地方？
哦，所以它这边就前面是 vector，它这边
因为知道，你看，
这边是一个 vector，然后这边都是 vector。
对啊，你看这边，它这边是写 CS 加 IS， 它里面都是存 CS 加 IS，
加
就是 post segment 加 instruction pointer， 只要我们有这两个东西，就是 point counter 的意思。因为我要知道我程式码从哪开始执行。
point counter 是
对，只是不同叫法啦。point counter 跟 instruction pointer 都有人交错的叫。
所以 counter 实际我们在写程式的时候，这个我们会教到这个东西吗？
我觉得这个比较看你是用什么计算机架构，但是我觉得这个你可以把它想成是可以互换的，对了。
所以从那开始，
对，
然后这个 CS 是 content
code segment 就是这个我觉得比较细，基本上 CS 加就是这个 instruction pointer 或 point counter，它就是可以定位出
是那个
code segment， 就是 COD 然后 segment。
OK，
对。但基本上这两个合在一起是可以让你知道说你的程式码放在什么地方。
是构成address。所以它构成两个东西，构成这个东西。那我想问，考试会细考它的东西吗？
可能会。对。好。
刚才说还会先找题，
对。
你找到会找 MAU，
没找到的话是 MAU 会帮你去做转换，因为它这个转换其实是今天你有一个 virtual address 它是64bit， 那我要怎么去找出它的 physical address 的长什么样子？虽然是从一个64bit 转成另外一个64bit 的样子，然后透过 MAU 去做操作动作。对。
他是说就是转换之后它会存进去。
对，因为它转换其实就是一个64bit 转64bit 的结果，所以它就会把它直接写到这个 TOB 里面去。
所以 CPU 都还是只有一个 TLB， 就是互动。
没有。CPU 会先问 TOB， 我就应该这样讲，就是这两个东西都是包含在 CPU 里面的。然后它的流程是，它会先找 TOB， 那没有的话，它会请 MMU 去做转换。对。
所以还是从 TLB。
对，因为 TOB 如果有的话，它就不需要做 MMU 的动作。对，MMU 做什么事情，下一班应该会讲。对。
刚刚在讲 TLB。我说刚刚这些讲课是在讲 TLB。
没有，整堂课是在讲，就是在这个机体管理上面应该要怎么做。
后这个指令，然后我确定就是我要的东西在哪里。那时候
没有这个指令是你写程式码的时候，它会宣告一个位置给你，让你可以做使用。
那说这 update page table，
就是因为这个指令，这个宣告是实体机体上会宣告一个区域出来，可是它会对应回去你的程式码里面的虚拟机体位置，然后它就去更新这个 page table。
是我写程式的时候。
对，
写程式的时候。
对。
请问一下，这边在 course 身后的部分，它这边的顺序上就是先把 system code number 先放到 EX， 然后再去叫 system code 这个映射的插巴里。
没错，所以这边其实应该是倒过来，
所以顺序上应该是要倒过来。
那 EX 是什么意思？
对，EX 是一个增存器。
增存器。
对。
所以是我们要在呼叫之前，先把你要用的 system code 先把它放到这个单纯器，
没错，
然后再。
其实这应该是一组的，就是这个 instruction 是放到某一个 register， 然后这个 EX 会填入这个 system code，然后再去执行它。对。
分享，谢谢老师。
这样。这Right. So let's come back. So I think there is an interesting question in the chat box. Is okay. As in this example, we say this one, ISR 0 vector is 4 byte. And why this is 4 byte? So the reason is this assumption is we run on a 32-bit systems. Okay, so on the 32-bit systems, like for the code segment and instruction pointer, they both will combine together and then the size will be 4 byte. Okay, 4 byte means 32 bits. So each code segment plus instruction pointer, it will occupy 4 byte. Okay, so this is the reason why this is 4 byte, not other bytes. Okay, but this is a concept. If we're in a 64-bit systems, it might not be 4 byte, but like even it is larger, it doesn't matter. Then the thing is just like if it is larger, then this step interrupt vector number will times a larger kind of number here. Okay, so this is just for a positioning about where is the instruction pointer is. Okay. So so let's get going. Like there are first bit, best fit, and worst fit, and then how to know how good they are. So actually there is a thing called fragmentation. Like if you doesn't really do a good allocation, or like if there are some like long-term, like when you use a system for long-term, then probably there will be some places they cannot be used, and that is called fragmentation. So the first one is called external fragmentation. So external fragmentation means like you have enough total memory space to satisfy a request, but the available spaces are not contiguous. Okay, so it means like, for example, you have if processor one look at this slice, and processor two has this size, and then we have the third process, and maybe it only needs this size. And actually the white part, the summation of white part can fit P3, but because we don't have contiguous space, so P3 cannot get the space. Okay, so this is called external fragmentation. And oh, sorry, I think there is a very important thing I didn't let you know is when we are doing this kind of addressing things, this memory management things, actually each patch frame should be continuous. So this is the reason like this. Each patch frame, they should be on the physical address, they should be continuous. So for example, this patch frame A, they cannot be split into two other patch frame. Okay, so the reason that should be contiguous is it will be easier to be addressing, and it is easier to get where it is. Okay, if this is not continuous, then we need extra management overhead. For example, we need another data structure to keep track of where is the another like their related patch frame is. So this should be continuous. And also for the virtual address space mapped to this physical address space, that should also be continuous. Okay, so for a patch, both the virtual address space and physical address space should be continuous. There should be a continuous 4 kilobyte area. Okay, so this is very important for the design of the pageant. Okay, so this is called external fragmentation, and internal fragmentation I think is quite easy. Just like it occurs when systems split the continuous space into continuous chunks. Oh, sorry. For example, like if we have a like 4 KB area, right? But actually inside the 4 KB, you only store like 3 kilobyte of the space, and you let 1 kilobyte there. then this is called internal fragmentation. Okay, so this happens even you are using pagination because each page is 4 kilobyte. So if you use, I mean, if the data is smaller than 4 kilobyte, then there goes the internal fragmentation. Okay, so if you are going to solve the internal fragmentation, in most cases, you need a smaller page size. But smaller page size means you need more overhead to manage it, right? For example, coming back to the page frame overhead, I mean, this page frame, each page frame is 4 kilobytes, so they have those kind of fields here. So after some calculation, we know we need 40 bytes to manage this 4 kilobyte area, right? But if you string the page size to only 1 kilobyte, then the size is also 40 byte. But for this 40 byte, you can only manage 1 kilobyte. So the overhead will become 4 times larger. Okay. So the reason why we care that much about this is 40 byte because this structure should be also put on the memory. So it also consumes memory. And this 40 byte is just about, I mean, they're just here, few counters here, but in the real system, if there are more counters, then 40 byte will go up. Okay, so it really takes some overhead if we shrink the page size to a smaller page size. Okay. Okay, so this is for the external and internal fragmentations. Okay, so I think those are about the things we learned in the undergraduate. And now let's talk about how Linux manage this kind of physical address. So actually, Linux manage this kind of physical address in a little bit different way. So first of all, we need to define a thing called zone. So the kernel uses the zones to group page frames or similar properties things together. So like this. Usually there are 3 kinds of zones in Linux. The one is called zone-DMA, and then zone-normal, and zone-high memory. Okay, so zone-DMA, it is about the very beginning of the memory, like it is between 0 megabyte to 16 megabyte. Okay, so zone normal is about 16 to 96 megabyte. And then zone high memory will be larger than at 96 megabyte. Okay, so maybe you will be quite curious about why we're going to split the zone into this kind of different property things. And this is because in the old systems, I would say like maybe 20 years ago systems, actually DMA is quite very, I would say like spatial settings there, because for some DMA settings, they can only support the first 16 megabyte of the memory. For example, if you are going to move the data, like the networking data to the host systems, and if you use DMA in the old system, you can only use the first 16 megabyte of the host memory. You cannot use more than that. The reason is because in that times, the DMA, the DMA is a hardware design, but there is some register inside the DMA. So there are some limitation there. You cannot flexibly use the whole host memory. Even you have like 16 gigabyte, you have like 64 gigabyte there. But at that time, when you are using DMA to move the data from storage device or like network device to the host memory, you can only use the first 16 megabyte. So due to this reason, at that time, Linux say, in this case, let's allocate, let's reserve the first 16 megabyte for this DMA usage. Okay, so this is the reason why we have zone-DMA. And zone-normal, you can think about most of the kernel related code or like most of the kernel related information, they will be placed in this area. So this is about the top. If you still remember, when we're using the 32-bit systems, kernel will use the top 1 gigabyte of the virtual address space, right? So this is the SAM. The zone-normal, they are alluding, they are saying from 16 to 96 megabyte as for kernel data structure. Okay, but we'll talk about this a little bit more later because I think this is quite complex. So you can just think about, hey, now zone-normal is for kernel, and zone-high memory actually this part of memory, just like more than x96 to whatever your system is, just like if it is a 16 gigabyte and this will be at 96 megabyte to 16 gigabyte, then zone dash high memory, like those kind of memory space, they're allocated to zone dash high memory. And the reason for that, why it is called high memory is because the lower 1 gigabyte, they are preserved for the, the upper 1 gigabyte, they are preserved for kernel. So the rest of it, they are for the user process. Okay, and there are more details later for this part. Okay, so here are the explanation about what's the function for each kind of zone is. Okay, so the second thing you need to know is there is a concept called node, and we will put the zone, node, and patch together later. Okay, so the reason like why Linux needs the concept of node is because in current system there are two different ways to access the memory. One is called uniform memory access. The other is called non-uniform memory address. So maybe you heard about it called NUMA. Okay, so uniform memory access just like this. So in the very traditional systems, like at that time on the motherboard there is a node bridge. So on node bridge there is memory controller, and memory controller can help the CPU to access the DRAM. Okay, so this is the old system. You can think about maybe like 10 years ago or like more years ago. And then current system, they move the memory controller into the CPU. Okay, so it looks like these kind of things. Just like each CPU has their own memory controller, and then they can connect to the DRAM. Okay, but the thing is, actually the CPU on the left-hand side can still access the DRAM on the right-hand side, right? And the way to get the data from the DRAM on the right-hand side is CPU on the left-hand side will first communicate with CPU on the right-hand side, and then to say, can I access your DRAM? And then after getting the permission, CPU on the left-hand side can access the DRAM on the right-hand side. So this is called NUMA because it is non-uniform memory access. For this CPU, accessing DRAM on the left-hand side is faster than accessing DRAM on the right-hand side. And the latency gap usually is kind of 2 times. The reason 2 times is because, first of all, CPU needs to talk to all CPU. And then the DRAM, the data should be moved from one CPU to another CPU. So it takes a little bit higher overhead here. Okay, so there is local access and remote access here. And maybe you are thinking about why we are going to move from a UMS system to the NUMA system. There are several good things for NUMA. First is about it has faster local access because this DRAM is directly stick with this CPU. Okay, so the bus is shorter. But if you look at the left-hand side, the UMS system, actually here comes a bus and here comes another bus. So usually there are 2 buses. So when we talk about the data transmission, when the bus is longer, when you have more bus to get to the destination, then you will get longer time. So shorter bus always get better performance. So this is the reason why when you have a CPU in the systems, and then you usually place your DRAM near the CPU. And your SSD usually will use like the PCIe, these sort of things to connect to it. And PCIe is longer than DIMM, right? Because DRAM DIMM is stick very close to CPU, so they can get better performance. Okay. And then NUMA can have better bandwidth. So the reason I have better bandwidth is because on the left-hand side part, this memory controller should control all these kind of DRAM requests. So you can think about if there are million requests to be sent to this DRAM, then this controller should take care of this kind of million requests here. Then this controller will become a bottleneck here to manage this kind of service. Okay, so this memory controller you can think about just like a very tiny CPU to do some decision about if the CPU 1 is going to get the data from DRAM 1 and CPU 2 is going to get the data also from DRAM 1, then how do I do the scheduling? Okay, so actually this kind of memory controller here will do some scheduling things, and then it's going to avoid some like package congestion there. Okay, so Yep, that is about NUMA and UMA. So nodes come like this. So nodes maintains a data structure for each NUMA node. So one NUMA node you can think about just like one CPU. So in here there are two NUMA nodes. There's one CPU and there's another CPU here. Okay. So first of all, when we are going to allocate the memory, actually we need to be aware of this structure, right? Because we know the DRAM near the CPU get faster time to access it. So when CPU needs the memory, usually we need to allocate this DRAM to the CPU, right? Otherwise, if you allocate this DRAM, it is also possible, but it takes longer time to access it. So node is quite important here. Okay, so let me give you a overview about what's the relationship between nodes, zone, and patch frames. So nodes will be at a very top tier because each node we need to allocate the DRAM nearest to inside each node. Okay, so for example, for this node, we will allocate this DRAM. But I mean, if this DRAM doesn't have enough space, then we will allocate other DRAM. Okay, but actually, this is only two node systems, and there are some server that will have 4 nodes or like more nodes there. So the network topology will become more complex if there are more nodes. So we need to manage in a node aspect first, and then it's zone. So you can see like for each node, under each node, there are 3 different kind of zones. Because for zone DMA, this is for very spatial usage. They're only for DMA usage. So we cannot allocate the first 60 megabyte of the DRAM. So we need this kind of zone concept to manage these kind of things. Okay. And then under the zone, there's patch frames, right? Okay. So because zone is usually larger than like the patch frame, this kind of granularity. So this is the hierarchy for the Linux to allocate the physical memory. Okay. So question? Okay. So let's talk about how to allocate the patch frame. So actually, Linux doesn't really use best fit or like worst fit or worst fit. Linux use things called body system to allocate the patch frames. Okay, so there is a function in Linux is called allocate dash patches function to allocate a single patch or more than one patch to the process. Okay. And if you have some sense about Linux, actually, there are also bite-size allocations, and they're using some other kind of functions here. But I think there is a kind of overall picture about the memory allocation. So usually we will split the application into 2 sides. One is called user space memory allocation for the user process. And then there is a kernel space memory allocation for the kernel side, okay? And there is a physical DRAM here. So usually there is a allocate patches layer here, and this layer they are using body system. So this is, people will say like this is a low level memory allocator. So we can get like single patch or multiple patches at this layer. Okay, so above the allocation layer here. For kernel, actually they can use 2 different sizes to do the allocation. One is about the K memory allocation. You can get a smaller size, or you can just directly get from the allocation pages. Okay, so there is a thing called step layer, and we'll talk about it later. Okay, so there is also another thing is if the kernel is going to get a larger size from the physical DRAM, we can use this kind of V memory allocation. Usually we're going to allocate like several megabyte or like gigabyte, and then we can pick this kind of virtual memory allocation. Okay, but the things that you know is for most of the kernel data structure, in most cases, we will go for this K memory allocation. So what do I mean? If you still remember, here, this is one data structure in kernel. And I said this is a structure pages data structure, and there's 40 byte right. So this 40 byte, if we are going to allocate a place to put this data structure, usually kernel will use this K memory allocation function to allocate a 40 byte to store those structured patch. And the same things, I mean, if you already learned about like text structure, data structure, those kind of data structure, they are also using K memory location to get the memory space to store those data structure. Okay, so there's another branch is a user process. So user process, they will use, I use C library here, but I mean, there's other kind of compiler, they do the very similar things. So for the C compiler, C library, actually there is a memory allocation function here. And then there are two different ways to get a memory. One is called mmap, another is called BRK. So both of the function can get the memory. So usually when we are going to get a larger memory space, we'll use mmap. And if we are going to use like heap, these kind of things, usually we'll go for the BRK. Okay. So let me focus on the allocation patches now. So actually there is a list here, and let's directly look at the example. If a process requests a 2 to the 2 blocks, so you can think about if a process needs 4 patches, but there is no free patches in order 2 and order 3. Okay, so this order actually means like 0 means 2 to the 0, so a 1, and 2 to the, and 1 is called mean 2 to the 1. Okay, 2 to the 2, 2 to the 3. So like this. So for each block means like for each 4 kilobyte patches. And then if we are going to get 2 to the 4 means with this layer, there are 16 patches here, right? So if there is no patch in the 2 to the 2 here, and there is also no in the 2 to the 3, actually the body system will get from a larger order. So we will always get a larger block and then to split into the half for the allocations. So if we are going to get 2 to the block, like 4 patches now, and there is no free space in order 2 and order 3, then we will get from order 4. So inside order 4, when we do one allocation, we will directly get 2 to the 4 block. And here, block and patch, they can use interchangeably. So block means patches. So for the level 4 here, actually, kernel will directly get 16 patches directly. But we will break this 2 to the 4 to half. So you can see like after breaking into half, we will keep 2 to the 3 at the order 3 layer. And we will allocate another 2 to the 3 to the lower layer. So the left-hand side of the 2 to the 3 will be kept in the order 3 layer. And then the right-hand side of the 2 to the 3 blocks will be moved to the lower layer. So this is 2 to the 2. Okay. So because the 2 to the 3 can be breaks to 2 to the 2 blocks. So after these iterations, if the system is going to get 2 to the 2 block, the system will directly return these 2 to the 2 blocks. And at this moment, in the body system allocator, in order 2, we have 1 2 to the 2. And in order 3, we have 1 2 to the 3. And then in order 4, like there is no, because they are allocated to the lower level. Okay, so we always get a larger one and break into half and then to do the allocation. So the reason like we also do the half allocation is because it is easier to do the maintenance. Okay, what I mean maintenance is, for example, if we are going to deal with the fragmentation, this will be an easier way because they are all following the 2 to the order mechanism. Okay, so you can think about if now we are not using this 2 to the order, like you can get any size, then probably there will be a lot of external fragmentation there. But if we use this kind of 2 to the order, probably we can alleviate the fragmentation issues because they are all in a block of the patch size. And then they are all half and half and half. So you always can get a larger one, and then a larger one can always break to a fixed size of the lower one. Okay, so this is the way like Linux thinks it is possible to deal with the external fragmentation by this kind of body systems. Okay. Okay, so there's another concept is about slab layer. So slab layer is here. This is slab layer. So the location patches we use body system to always split the larger blocks into half and then to check if it fits for the request or not. If it doesn't fit, then we will split into a smaller one. Okay, so when we go one layer above the location patches, there is a step there for the kernel side. Okay, so what does slab layer for? So actually, slab layer is for storing those data structure that is no longer needed, is returned to the free list instead of deallocated. So let me give you an example. Okay. So one cache is for like process descriptor, for example, and there is maybe another cache, maybe is for the file object, and the other is for the like a structure cache. So different cache in the slab layer, it means it is designed for different data structure. Okay, because different data structures, they have different sizes. For example, process descriptor maybe is in the size of the 100 byte, and file object maybe it is in the size of the like 10 of the 100 bytes, for example, like this. So different data structure, they have different sizes. So we need to have different like cache to deal with it. Oh, this cache is not equal to like CPU cache. No, they're not the same. This cache is just defined by step layer. So step layer define their cache structure. And here, so this is the text structure, if you still remember. And then actually, if you check the Linux kernel, there is a semaphore data structure like this. So actually, in a slab layer, each cache can maintain one data structure. So each cache, maybe there is a lot of process descriptors, then you can think about the cache will be quite large, and they will have spaces to put each of the process descriptor on the memory. Okay, so this is the inode. So actually, different kind of data structure, they will have different sizes. So this is the reason why they are split into different cache. So, okay. So when the available memory is low, there is no way for the kernel to communicate to every free list that it should shrink the size of its cache to free up memory. Okay. So slab layer acts as a generic data structure cache in there. I think this sentence is quite important because for using slab layer, actually, when you can think about when we are going to deallocate one process descriptor, right? If one process is terminated, then at the end of the termination process, we will clean up the process descriptor. But for example, if this one is like 800 byte, and we deallocate this 800 byte, then actually, if next time we are going to use up this 800 byte, it will be not easy to use because different data structure will not really fit this 800 byte usually. Then there will be a fragmentation. So an easier way is let's just keep the 800 byte for the next process descriptor because each data structure, they will be in the same size. So no matter which process, their process descriptor, for example, will be 800 byte. And for no matter which file, their file objects will be in the same size, for example, 100 byte, for example. Okay. So different data structures, the same data structures for different process, they will still have the same size. So the key concept behind the slab layer is to be used as the generic data structure cache in there to cache in different data structure. And the reason like Linux wants to have this kind of design is because frequently used data structure tends to be allocated and free often. So if we can have this kind of caching-like design, then we don't need to worry too much about the fragmentation. Okay. Once again, this cache is not CPU cache. So this cache is just defined by step layer. Okay, so they're different. Okay, and there's another reason why we need this kind of generic layer is because kernel data structure is usually smaller than a patch because patch is still too large for the data structure. Patch is 4 kilobyte, but data structure, the sizes vary, but probably it will not larger than 1 kilobyte usually. It's just several bytes there. Okay, so frequent allocation and delocation can result in memory fragmentation. So if we can maintain this kind of slab layer, we can deal with this memory fragmentation issue. And also this slab layer can be met per processor. So no locks are required for allocation and deallocation. And it also can be NUMA aware, like these kind of things. Okay. So how slab layer works? So the key idea for the slab layer is to avoid from allocating and freeing up physical address as frequent as possible. So actually, the structure will look like this. The structure is cache, slab, and patch. So one cache per object. So for example, what I mean object is, for example, for text stack structure, inode, semaphore, they will be classified into different cache. So there is a text structure for getting one cache, and under this cache, they can have a lot of text structure related to belonging to different process. But this cache cannot be used to store, to accommodate the inode or semaphore. Okay, so inode has their own cache. Semaphore has their own cache. Okay, so like this. And okay, so inside this cache, there are several lists. There are 3 for them. One is full, and then partial, and then free. Okay, so full is like this, just like for the patches, they are used for this slab cache, and in this patch, there will be partition to split into this kind of text structure, right? Because each patch is 4 kilobytes, but each text structure probably will be like only several hundred bytes here. So in each patch, we can store several text structure inside. And what we call full is if there is no free space for a new text structure, then this is the full slab. So there are use. Okay, so what do I mean for partial is when there are some text structure, they are deallocated or like they're unused, because if there are some process that are terminated, then the corresponding text structure will be unused. Okay, so actually when one process is terminated, we will not remove the text structure right away. We will leave it. We will just mark it as unused. And then if there is another process, if there is new process, they are forked by their parents and they need a text structure, they can directly grab a space from the partial and they can directly use it. Because they are all text structure. The only difference is for the field in the text structure, they are quite different. So the difference will only be maybe for the first field, previously it stores like 1, and then for the second field, and then for the next process, the field will be changed to store like 2. So the layout for the data structure is the same. The only difference is just the value for each field is different. So it is possible to directly reuse the space. Okay. So actually there is a scenario is if for this lab, actually there is called empty list. It means like all of the text structure inside there are unused. Okay, so in this case, it is possible to have one choice is to directly reclaim this lab. It means like all the text structure there becomes unused. So maybe we can directly erase or like to deallocate this memory to other usage. Okay, so this is the concept for this kind of slab there. Okay. So for the allocation, only when there does not exist any partial or empty slab in each cache, we will do a new allocation. Otherwise, if there are some like partial or like empty, and we can just directly reuse those space. We don't really need to do a new allocations for slab there. Okay. Okay, so when we free the slab, only when the memory utilization is quite low, and then there are this kind of empty slabs, then we will free up this kind of empty space. Otherwise, if the memory we still have enough memory in our systems, we will not do the free. Okay, because just put it there, and one day if there is process they are created, we can just directly reuse this text structure. We don't need to do the construction there. Okay, so it will save sometimes, because if each time we do the fork and we are going to do copy on write, and after copy on write, we are going to construct a new text structure. We need to do the allocation. We need to ask for, hey, is there any free space to construct this text structure? So it usually takes time. But I mean, if the text structure are already here and we can just reuse them. Okay. So later on is like the two kind of memory allocation provided by the kernel. One is called K memory allocation, kernel memory allocation, and the other is V memory allocations. So K memory allocation function obtains like kernel memory in bite-sized chunks. So there's just a note, just like to let you know, as you already saw in this figure, like what you usually see is memory allocation is on the user side. So when you are writing a kernel function, when you are writing a kernel drivers, these kind of things, there's no memory allocation function there. You need to use either this one or this one. Okay. So, okay. So if we need a full 4 KB page, allocated page in prior slice fits better. And it returns a pointer points to a block of memory that is at least the requested size for when you're using these K memory allocations. But I mean, if you are going to get more of it, then you can use this kind of, sorry, if you are going to use a smaller one, not like 4 kilobyte, you can use this K memory allocator. Like they will call a step function to help you to do the memory allocation. So K memory allocation in this figure, it works with the step there. Okay. And then V memory allocations is like this. It allocates memory that is only virtually contiguous. Okay. So it requires patch table to maintain a mapping between virtual and physical address. Oh, the reason I say virtually contiguous is not like you can allocate a size smaller than 4 kilobyte. I mean, it is, if you want like 40 kilobyte, for example, then you have 10 4 kilobyte pages. And these 10 4 kilobyte pages doesn't need to be contiguous. Okay. They can be in different, I mean, address space. They can be in different space because we have a patch table. The patch table can keep track of where is the patch is. Okay. Okay, so actually just like allocate virtual memory initially and then map to the physical memory on demand. It's quite the same as the user level things. Okay. So regarding performance, memory allocation inside kernel usually use K memory allocation. So the reason is K memory allocation, in most cases, it's just about to reuse the prior slab. So it doesn't really need to do too much of the allocation and maintenance. But if you are going to use these V memory allocations, then there's the patch table things here. We need to manage the patch table. So it takes way more time than K memory allocation. So I'll give you an example about how K memory allocation works in the next slide. So if system can get enough continuous physical address all the time, then there is no address translation overhead. So what does this sentence mean? So it means like if the space of the if the space of the virtual address space and the physical address space is in the same size, then we can directly do one-on-one direct mapping. We don't really need a patch table there. And the reason why we need patch table is because virtual address space provide us to use the space larger than physical size, right? So you can think about when you are writing a program, you don't really need to care about what is the size of the physical memory, right? So when you are writing the program, you don't really need to care about how many users are there in the systems. But come to think about it, even each process in a 32-bit system, you can get 4 GB of the virtual address space. But if there are like 100 of users that have 100 process there, then can each process still get 4 GB of the address space? it is not possible, but virtual memory, that is possible, right? So this is the reason why when you are writing a process, you don't really need to care about how many users are there, okay? But if you still remember, kernel address space that share between user address space, right? Because kernel used as the top 1 GB of the memory address space. So no matter which user process, they will allocate their first top 1 GB for kernel, and this is quite important. Okay, so why it is important here? So let me show you. So on a 32-bit system, what if the kernel consume more than 896 megabyte of memory? So before answering this, let me show you one thing. So this is virtual address space, right? When you are writing a C program, actually what you can get from memory allocation, those kind of things, they are from virtual address space. Actually, you don't really know what is physical address space, because physical address space, they are masked from the user. Only the DRAM controller can know what is the physical address space is. So for this virtual address space, actually the top 1 GB is for kernel. So actually when you are doing the programming, you cannot really program this part because this is for kernel. So when you are programming a C program, you can only use the bottom 3 GB. Okay. So for this top 1 GB, actually from 3 GB to 3.896 GB, they will use K memory allocation, and usually kernel code and data, they are placed here. Okay, so why it is like this? Because this space will directly one-on-one mapping to the physical address space here. Okay. So because all the process, they are having the same location like this. So actually this one can directly map to the physical address from the very beginning, 0 GB to 896 megabyte. Remember, when we are talking about like we have zone-DMA and zone-normal, actually zone-DMA means the first 16 megabyte, they are zone-DMA. Okay, and then from 16 megabyte to 896 megabyte, therefore zone normal. Okay, so even this example just for 4 GB, but you can still thinking like, if this is a 16 GB or like 128 GB, the first 16 bits, they are still for zone DMA. And then later on zone normal, there will be for the kernel function. Okay, so why this is so important here is because here, this one is at 96 megabyte, and this one is also at 96 megabyte. So the virtual address space is in the same size of the physical address space. So we don't really need two complex patch table here. We can do one-on-one mapping. What do I mean for one-on-one mapping is like this. We can do direct mapping. Physical address equals virtual address plus some offset. Okay, so this is virtual address. So actually, if we do add some offset, we can just ship to this. What do I mean for apps offset? You can think about maybe just like to minus 3 GB. So here, if we minus 3 GB, all the address can be directly mapped to this, right? And we don't really need to check what kind of patch table is actually. I mean, there do have a patch table, but it won't be very simple because just like every address, they just minus 3 GB. And for this address space, you can be mapped to here. Okay. So why we are doing like this is because when you are running the kernel, you don't want to take too much of time to run the kernel. And if each time you need to do the patch table translation, each time you need to check the TOB, it will take a lot of time. But now, if you can just, CPU can directly calculate, okay, where is the physical address is, and you don't really need to touch a memory, actually it will save a lot of time. So this is one of the reasons why in Linux, they design their kind of kernel space, they should be shared between all the processes. Okay. So there are still like 128 megabyte, they are not used. And they're not used is because this 128 megabyte, they are used for dynamically mapped to the rest of the high memory part. Okay, so for physical memory, we only use at 96 megabyte for the kernel code, and all the process they share this 896 megabyte, but above 896 too. Depends on how many memory you are using in the system. It can be 4 gigabyte, it can be like 64 gigabyte, or like it can be more. I mean, there's a large memory space here, right? Large physical address space. So probably we need some translation there, right? It cannot be one-to-one mapping because it is not possible to do the calculation. So we need to have some way to do the like patch table management to know, okay, so where is the data is in the high memory part. Okay. So high memory is not permanently mapped. It can be temporarily mapped to here, zone high memory. So for each virtual address space, they have 128 megabyte of this space to do this kind of virtual mapping. So how to use this kind of high memory in Linux? Actually, just about to set out a flag in the allocator. So there is a gap-free patch high memory. Then we can have this kind of this flag can be set at a V memory allocation. Then you can allocate for the high memory. But actually, the thing is like this. Actually, this is because in 32-bit system we only had 32-bit virtual address space, right? But in a 64-bit system, actually we have 64-bit virtual address space. 64-bit means you have several gigabyte to or even terabyte of the address space for mapping. So actually in current 64-bit system, we don't really use this kind of high memory because you have way more kind of address space here. But I mean, this is just quite interesting to let you know at the history why Linux is going to use this kind of 1 gigabyte space and how to place this kernel here. Okay, so yeah, that's it for it today. So see you guys next week.
virtual 大于 physical
没有，哦对了，如果你要这样讲也是没错，它不能说大于，就是它用不完。它不能说大于，就是它用不完。因为32bit 是你只能定值2232次方，所以2232次方是4096 KB 左右，4096 GB 左右。所以这边的 example 抬头是4 GB， 可以有64的话就是264次方，所以那是好几百 TB 以上。它还是会用完啊，就是但是它一般正常人是使用不完的。对，
然后你说是哪一个最大？就是virtual还是？但是virtual是比它大，一般是virtual。
你说一般吗？如果是64bit的话，就是 virtual 比较大，但是你要插到比 virtual 大也是有可能，就你可以不断插机体，它就会比 virtual 大。
哦，
对吧？就看你。
刚好像电脑上看到是，那一般是几 GB？
我觉得看吧，就是有 server 是插到机体的。对啊。
我现在都不会用了。
会啊，还是会，因为kernel是从以前映射到现场，所以它需要向前相容。所以其实有很多kernel设计是好久以前为了某一个硬体架构底下出来，就像你说那个这种 DMA， 现在也都还有。所以
用 K memory location 是可以去控制 kernel 的。
不是控制，是它可以去分配机体位置给 kernel 来做使用。
哦
kernel 我知道结构。
我可以去动 physical address 的 mapping， 可以动的吗？还是说这个分配？
就是你如果去改 kernel K memory location， 确实是可以去改，但你要改它的 kernel 里面的这个 library。对。
数学上的那个。
啊，是没有，它就是用804这么去做而已。
哦，
对。
这边我听不太懂，为什么说是就是 return freeze， 就是说它不是把所有资料全部杀掉，
没有。就是因为你这个 text structure， 你可能假设80 byte 好了，对，可你用完之后，你下个 process 来还是用那80 byte， 对吧？对，那你就不用把它删掉了，就下一个 process 来建的时候，你就直接用前面那个人的，就不需要重建。
哦，所以有些变数
就是变数，你只要改那变数值就好了，但栏位是一样的。
改 value，
对。你要不要先问？
想问就是上堂课讲这个为什么这个时候？
因为他在做查找的时候，近乎是 O1 的时间，因为他只需要看说你这个里面。第一个在哪里？然后这里的话，基本上它是1就代表它在 Q1 地方，这样。那 Q1 地方它只要找 Bible 去找，所以基本上每个操作都是近乎 O1 的操作。
所以它 进入 OS 之后，就是我要再插入一个 process 的时候，
哦，它是在讲的是搜寻的时候，
搜寻的时候
对，，因为你这个地方它其实只需要用一个特殊的 CPU 指令，它就可以直接跟你说这个32 bit 里面第一个被 set 起来是谁。然后因为第一个被设起来，它就会有个 index，那 index 拿在这边，只要去查它是哪一个 array 的，然后它只拿第一个，所以基本上每一个操作都是 O1 就可以完成。
然后插到第一个就可以。
哎，对对对，
好，漂亮。
我想问，其实有点 pretty much 就是今天上课，就是我的整个架构有点不太清楚，就是
你说
OK，像这个 preference 这些都是 physical agents，
都是 physical
就
agent，
是很像 different agents。
对
那所以 physical agent 里面会有 hash table，
，physical address 里面对吧
会有
？hash table 是在 physical address 上，对，
那所以那一个就是像这个的 data structure，就是40 byte
对，
的这个 data structure，都是
对
放在
一个 parent 上面，
parent 里面吗？还是
它可以放在对，它可以放在一个 parent，对，
但它会跟它就是 describe 的 parent 是放在同一个地方吗？
不一定，
不一定，
通常不会，
通常不会。
对，
那所以假设我今天 create 一个 process，
对，
然后它要 allocate 一段 memory 的话，它就会 allocate 2段，就是一段是 for 这个 scripter，
没错，
一段会是 for 那个
没错，它自己那个 process 要的那个空间，
OK，
所以它有分 meta data 管理跟一般正常 data 管理。
然后，所以刚刚这个 slab 就是一个 process 它拥有的那个 address 就是 patch frame 的数量，有点类似这样。
有点类似这样，对。
哦，
但其实，对啊，你要这样理解也是对的，就是它是一个 page frame 里面可能去切出好几个，都是同样40 byte 的空间去做使用。
OK，一个 patch frame，
对，
然后也有可能还有其他的 page。
对。
OK，那我想，
等下，我先出去好了，等一下我们再继续在外面讨论一下。
再去教室那边。
对，因为下个老师来了。